Hello, today we are going to start a new topic, a new course in classical mechanics in the channel. We are going to start talking about the Hamilton-Jacobi formalism. We will be making a series of videos that will pretend to explain further what is the Hamilton-Jacobi formalism and how to use it to find the equations of motions of so many different mechanical systems. So what we need to remember first to establish the first important thing, which is going to be the Hamilton-Jacobi equation, is that there is something known as canonical transformations. So what this is about? Well, we know that the Hamiltonian function depends on, well, the variables q, the variables p, and maybe the time. Okay, in a more general way, we can establish that we have n q's, like q1, q2, all the way up to qn, then p1, p2, all the way up to pn, and the time, where remember that these p's correspond to the conjugate momenta of the q's. Okay, so this is like the general expression for a Hamiltonian function. So the canonical transformations, they pretend to establish some new generalized coordinates for a new Hamiltonian function. It is not exactly the same as the Hamiltonian, but it is like an analog function that we are going to name with the letter k. Okay, so the letter k, this new function, will be a function of, again, some new generalized coordinates that we are going to name with the upper version of these little q's and little p's. It will be upper q1, upper q2, then p1, p2, all the way up to pn, and the time. Okay, so the canonical transformations consist in finding well, these new q's and these new p's in terms of the other q's and p's. So the canonical transformation can be established as q as a function of q1, q2, p, little p, 1, p2, all the way up to pn, and the upper p is going to be, well, a function of, again, these same variables, like this. Okay, so that means that if we are able to find these new functions q and p that represent a canonical transformation, well, that means that these new variables need to satisfy the Hamilton equations. Remember, the Hamilton equations for the regular variables are that qi dot is equal to the partial of h with respect to pi. Okay, and for the pi dot, it is like very similar but with a minus sign, and we take the partial of h with respect to qi. These are the very well-known Hamilton equations. So after making the canonical transformation, we can establish that the new Hamilton equations for the upper q and upper p, well, they are going to be exactly the same, but we are going to express them in terms of the new Hamiltonian function, which is the letter k that we have here. So that will be qi dot equals to the partial of k with respect to pi, and pi dot is going to be minus the partial of k with respect to qi. So that means that these new functions, well, they satisfy the Hamilton equations. Other thing that it is going to be very important to mention is that there are some functions that are going to be helpful to be able to find these canonical transformations. And these functions are going to be known as generating functions. Okay, so we are going to establish that f is going to be a generating function of canonical transformations in this way, this Q and this P. So the generating functions need to satisfy two things. If we are able to find this F, then Pi, little p, is going to be equal to the partial of F with respect to Qi. And Qi is going to be equal to the partial of F with respect to Pi. These are the upper Q and the upper P. And these are the little p and the little q. Other thing that needs to happen with this generating function after finding the canonical transformation is that the new Hamiltonian k needs to be equal to the original Hamiltonian h plus the partial of f with respect to time. Okay, perfect. So you also need to know that there are some particular cases where if we choose the correct canonical transformation, we are able to find a new Hamiltonian k that is going to be equal to 0. In that case, if we look to these two equations that we have here, looking that this k is equal to 0, then we can easily see that upper Qi dot is going to be equal to 0. And that means that this Qi is going to be a constant for all I. Okay? This is for I equals to 1, 2, up to n, and it will happen the same thing with the Pi dot. This is going to be equal to 0, and Pi is going to be a constant. This is going to be very, very important because later on we'll see that the Hamilton equation, the Hamilton-Jacobi equation, is going to lead us to the solution of the Hamilton equations. But for that to happen, this is a necessary condition. Okay, so if we take the k equal to 0, then we get that the Hamiltonian plus the partial of f with respect to time is going to be equal to 0. And remember, this Hamilton is a function of the q's, the p's, and the time. But remember that now we are saying that this Pi is equal to the partial of f with respect to Qi. So we are going to be interested in taking out these p's and express them in terms of the generating function f. So that means that we can use this equation to establish that this Hamiltonian function can be seen as a function of Qi. Let me use the letter I again, and then we will have here the partial of f with respect to Qi, and then the time. Okay, so we are just switching the dependence on the conjugate momentas to express them in terms of the partial derivative of the generating function with respect to the Qi coordinates. Okay, so if we take this expression into this equation and we name this generating function with the letter s, we said that f is equal to s. And why is that? Well, by now this is just a matter of notation. We are going to use the letter s just to be at peace with the notation on the book. But you should know that later on this s will it will represent the action of the mechanical system. But the action is something that we are not going to talk about in this lesson, but it will be important later on you keep studying classical mechanics. So for now, ignore that this S means that it is going to be the action. So now we are just going to write this Hamilton, well, this equation in terms of that S variable. So we are going to get that the Hamiltonian function is going to be a function of the Qi, then the partial of S with respect to Qi, then the time, and then plus the partial of S with respect to time is going to be equal to 0. And this is what is going to be known as the Hamilton-Jacobi equation, okay? Which actually is a an n system of partial differential equations, because remember that, well, we have an equation for every value of I. So that means that this is not one equation. This is actually representing n equations that, again, they are a partial differential equation, and actually it's an equation of first order. So it is important to identify what type of problem we are dealing with. It is a system of n first order partial differential equations. That will be like the conclusion with this thing that I have over here. So what we are going to do now is to see an example of how to use this Hamilton-Jacobi equation into a very famous problem, which is the harmonic oscillator. You know, every time we deal with a new topic in physics, we relate it with the harmonic oscillator. So that is what we are going to do now. Okay, so what we are going to do now is to establish that the function s, which is a function of q, upper p, and t, will be defined as minus p squared divided by 2m plus m omega squared divided by 2 q squared. It will multiply the tangent of omega t divided by omega plus p q secant of omega t. And we are going to see that this function is a solution of the Hamilton-Jacobi equation, where the Hamiltonian of that Hamilton-Jacobi equation corresponds to the Hamiltonian of the harmonic oscillator. Actually, that equation can be seen as this. It will be 1 divided by 2m that multiplies the partial of s with respect to q squared plus m omega squared divided by 2 q squared plus the partial of s with respect to time equals to 0. This is the Hamilton-Jacobi equation that is including a Hamiltonian that corresponds to a one-dimensional harmonic oscillator. I say that is one-dimensional because we only have one q. In this case, I is only equal to 1, so we have only one generalized coordinate q. So that is what I mean with one-dimensional. And here, look that if we change this partial derivative of s to maybe a p, we will get the regular Hamiltonian 1 divided by 2m p squared plus m omega squared divided by 2 q squared, which is very known that this is the Hamiltonian of the harmonic oscillator. So we are just switching the p by this partial derivative of s to get the Hamilton-Jacobi equation, just adding this partial of s with respect to time. So we are going to see that this s that represented the generating function, well, is a solution of the Hamilton-Jacobi equation. So what we are going to do now is to calculate the first term that corresponds to the partial of s with respect to q. So if we look to our expression, we see that the partial of s with respect to q is equal to, well, it will be minus m omega squared q, taking the derivative of this term, and it multiplies this term that is a constant, so it will be tangent of omega t divided by omega, and then plus upper p secant omega t. Perfect. And then, well, we need to calculate the derivative of s with respect to time, so that will be the derivative of s with respect to time equals to, by now this will be a constant, so we are writing the same thing, plus m omega squared divided by 2 q squared, and then we are going to take the derivative with respect to time of this. You know that the derivative of the tangent is the secant squared, and we are going to take out an omega when we use the chain rule, and this omega will cancel with this omega that we have here in the denominator, so that means that we are going to get here a secant squared omega t, and then plus pq, then the derivative of secant omega t, it will be tangent omega t secant omega t, and we take out an omega again, so let me write that omega here. Perfect, so that will be the derivative of s with respect to time. Okay, so we need to take this into the Hamilton-Jacobi equation. So that will be 1 divided by 2m times the partial of s with respect to q squared. So that will be minus m omega squared q tangent omega t. Actually, this omega can cancel this, so we get this. So like this. And then plus p secant omega t squared plus m omega squared divided by 2 q squared plus the partial of s with respect to time, which is all this quantity that I have here. Let me just copy to make it faster, like this. Okay, and let me close the brackets here. Okay, so if we make the calculations, we are going to get that this is 1 divided by 2m, and then m squared omega squared q squared tangent squared omega t minus 2 times m omega q p tangent omega t secant omega t plus p squared secant squared omega t, then plus m omega squared divided by 2 q squared, then minus p squared divided by 2m secant squared omega t minus m omega squared divided by 2 q squared secant squared omega t plus p q omega tangent omega t secant omega t. The first thing I want you to notice is that this term that is dividing, it is being divided by 2m, it can cancel with this term over here, and that this element is being divided again by 2m, so this 2m will be cancelled with this 2m, and it will be remaining an omega qp tangent secant, and that is what we have here, pq omega tangent secant, so this term will cancel with this term. Perfect, so we are going to get that, and if we multiply this element with this, we are going to get m divided by 2 omega squared q squared tangent squared omega t plus m omega squared divided by 2 q squared minus m omega squared q squared divided by 2 secant squared omega t. Perfect. So it is very easy to notice that we have a common factor here. So we will get tangent squared plus 1 times this, but tangent squared plus 1 is secant squared, and we have minus secant squared here with this also common factor. So it is easy to notice that this is going to be equal to 0. Just to remark, it will be m divided by 2 omega squared q squared tangent squared omega t plus 1 minus m omega squared q squared divided by 2 secant squared omega t. But again, by a trigonometric identity, we have that this is secant squared omega t, so it cancels with this. So perfect, it will be 0. And that means that this function s, well, it is a solution of the Hamilton-Jacobi equation for the harmonic oscillator. Okay, so after finding the solution, then we can say that this s is going to satisfy these two equations that we have here, that pi can be found taking the derivative of that s with respect to qi, and that q can be found just taking the derivative with respect to the p element. Remember, we named this f as s, so f is the same as s. So that means that we can find that pi is equal to the partial of s with respect to qi, and qi is equal to the partial of s with respect to upper pi. Remember, in this case, looking that it is one-dimensional, our problem, we can just erase this I like this. So after finding our s, well, just to find the p, we need to take the derivative of s with respect to q. But actually, that is something that we already found. So the partial of s with respect to q is equal to this, So this will be our little p. Perfect. Let me copy this to take it into another place. Okay, there it is. And now, making use of this second equation, we need to take the derivative of the s with respect to the upper p to get the q. So, okay, where is our s? Perfect. So what would we get if we take that derivative? Let me take this s to another place in the page to get some space. Okay, now here we have the s. So if we take the partial of s with respect to the upper p, we are going to get minus p divided by m tangent omega t divided by omega plus q secant omega t. And again, this is going to be the upper q. Okay, remember that the interesting thing of the canonical transformations is that, well, we need to be able to express the p in terms of the little q and the little p, and the q in terms of the little q and the little p. So we have here some functions that, well, they relate the p and the q, but we need to solve these equations to be able to express these upper variables in terms of the others. So that is what we need to do in this step. So if we look to this first equation that we have here, we see that it is very easy to express the upper p in terms of the little variables. We see easily that p is equal to p plus m omega q tangent omega t divided by secant omega t. So that means that this little p will be multiplying a cosine omega t, just p divided by secant. We know that this is p cosine. And then plus m omega q and tangent divided by secant. Well, we know that this is just the sine omega t. Okay, perfect. So here we have our first important result. This will be like the first part of our transformation. So we take the second equation, that is q in terms of the upper p and the little q. And to be able to express this q in terms of the little variables, we can just substitute this value of p that we just obtained, and then the remaining function will be a function of just the little p and the little q. So we get that q is going to be equal to, let's say, minus tangent omega t divided by m omega, and this is going to multiply little p cosine omega t plus m omega q sine omega t, and then plus q secant omega t. As you can see, we already have a function q that only depends on the little p and the little q. So this is going to be equal to, well, we have here minus p divided by m omega. Tangent times cosine is going to be the sine omega t. Then minus, it will be q sine times tangent can be seen as sine squared omega t divided by cosine omega t, and then plus q. And here, this q secant, we are going to see it as q divided by cosine omega t, just to be able to have the common factor in the denominator. So this is going to be equal to minus p sine omega t divided by m omega, and then it will be plus 1 divided by cosine omega t times, and here let me put a q, it will be 1 minus sine squared omega t. But we know that this is equal to cosine squared omega t just by the Pythagorean trigonometric identity. So cosine squared divided by cosine, it will be just a cosine in the numerator. So we will have q times cosine omega t here. Perfect. So this will be q equals q cosine omega t minus p sine omega t divided by m omega. And here is the q in terms of the little q and the little p. completing the transformations that we were looking for. So, okay, remember that we mentioned that when the new Hamiltonian K is equal to 0, this means that this Qi and this Pi are constants. So, if we are able to express the little p and the little q in terms of this upper Q and upper P, that will be equivalent to the solution of the Hamilton equations, because the Q will be a function of some constants and the variable time. So that means that that is a solution of the Hamilton equations for the Q. And well, let me do it to explain it. So we are going to start by solving this equation for the little q. So we are going to get that q is, it will be the upper Q plus little p sine omega t divided by m omega, all divided by cosine omega t, which is going to be equal to q secant omega t. You know that q divided by cosine is q secant, and then plus little p, sine divided by a cosine will give us a tangent, and then divided by m omega. So we have here a q in terms of upper Q and little p. So we need to find the little p in terms of maybe the upper P and the little q to be able to solve that equation for q and to see what are we going to get. So we are going to take now this second equation. We are going to solve it for little p. So if we do that, we are going to get that little p is equal to upper P minus m omega q sine omega t, all divided by cosine omega t. Remember, from this equation. So we will get that p secant omega t minus m omega q, it will be tangent omega t. Perfect. So we now have p in terms of this. So we are going to take this into this little p that we have here to solve for q. And then we are going to get q secant omega t plus p secant omega t minus m omega q tangent omega t. That is going to multiply tangent omega t divided by m omega. Again, this is going to be equal to q. So if we work with this, we are going to get q secant omega t plus p secant omega t tangent omega t divided by m omega, and then minus q tangent squared omega t equals to q. We are going to take this into the right hand side of the equation to take the q as a common factor, and then, well, that will give us q secant omega t plus upper P divided by m omega secant omega t tangent omega t equals to q that is going to multiply 1 plus tangent squared omega t, but we know that this is secant squared omega t. So we are going to take this secant to the left hand side dividing. So to get q secant omega t divided by secant squared omega t, and then plus p divided by m omega secant divided by secant squared, we are going to get tangent omega t divided by secant omega t equals to q. And this is going to be, well, we will have in the denominator a secant, but in the numerator it will be a cosine again. And then plus, we know that tangent divided by secant is equal to the sine. So we will get p divided by m omega sine omega t equals to q. Perfect. So this will be the first solution for the Hamilton equations. We know now what is the value of q as a function of time, which is equivalent to establish the solution of the the solution of the problem of the mechanical system that we are dealing with. Remember that always the objective is to find a function that tells us what is the generalized coordinates in terms of time. So that is actually what we do with the Lagrange equations. We take the Lagrangian into the Lagrange equations to get a function of the generalized coordinates as a function of time. So this is what we get, because remember that the Q and the key are constants. So we have a function that actually corresponds to the solution of the harmonic oscillator. Remember that the solution of the harmonic oscillator is a linear combination of sines and cosines. So that is what we got. Perfect. So if we remember, here we have the little p in terms of the p and the q, and now that we have the q, we are able to find the little p. So we are going to take this equation and we are going to replace the value of the q. So we get that little p is equal to upper p secant omega t minus m omega. Let me write the tangent here, and then the q. The q is going to be q cosine omega t plus upper p divided by m omega sine omega t, like this. So if we simplify a little bit, this is going to be p secant omega t minus, well, we have the tangent times the cosine, that will be a sine, so we have here minus m omega q sine omega t, then minus, it will be a p times sine omega t tangent omega t. But this can be seen as, looking that this is the sine divided by the cosine, we can see here sine squared divided by cosine omega t. And this secant that we have here can be seen as 1 divided by cosine omega t. And if we take a common factor p, we get p times 1 minus sine squared omega t divided by cosine omega t minus m omega q sine omega t. And yeah, of course, this is equal to the cosine squared of omega t. Cosine squared divided by cosine, we will get p cosine omega t minus m omega q sine omega t. And this is the function that describes the little p of t, of course. The second solution for the p's, the function p in terms of the time and the function q in terms of the time. So this will be an example to see how to use the Hamilton-Jacobi formalism and Hamilton-Jacobi equation to be able to find the equations of motion of a mechanical system. Again, in this particular case, we used it with the harmonic oscillator. Perfect. So those will be the important results of the lesson, and of course, the Hamilton-Jacobi equation. So this will be a good moment to finish the lesson.